So, in the previous class, we have discussed the case of a rectangular fin. We have arrived at the general solution of the rectangular fin, the general expression for the heat lost from the fin, and as I told you in the previous class that today we will discuss some of the special cases of that rectangular fin. So, in today's class we will discuss the special cases of rectangular fin also we will discuss the efficiency and effectiveness of fin, efficiency and effectiveness of fins. These two things we are going to cover in today's class. So, the first case is case number 1 is end of the rectangular fin is fully insulated. End of the fin, I am not talking about the root or base. So, end of the rectangular fin, because let us suppose this is the surface from which heat energy is to be dissipated and this is the rectangular fin. So, I am not talking about this portion, rather I am talking about this portion, that is the free end. So, when this condition is there, when rectangular end of the rectangular fin is fully insulated, so in this case the boundary conditions get changed as number A, theta is equal to theta 0 at x is equal to 0, that condition will remain unchanged because I am nothing considering the insulation at the base, considering the insulation at the farthest end. So, theta is equal to theta 0 at x is equal to 0, and since the farthest end is fully insulated, that means no temperature gradient will be there. So, the d theta by dx that is equal to 0 at x is equal to L. So, these are the two boundary conditions by the virtue of which we come to know that how the constant of integration as it appears in the equation number 5 of the solution of the rectangular fin, how it changes. Sorry, the equation number 2, that is the generalized solution, that is the theta is equal to C1 cos HMX plus C2 sin HMX, where C1 is equal to A plus B and C2 is equal to A minus B. How the value of C1 and C2 changes as the boundary condition changes. So, let us consider the boundary condition B. So, the expression for theta was, what was the expression for theta? That is, theta is equal to C1 cos HMX plus C2 sin HMX. Here in this case also the value of C1 that will arrive at theta 0, that is the theta 0 cos HMX. The only C2 will get changed in this case plus C2 sin HMX. So, differentiating this equation with respect to x, so we will obtain the d theta by dx that is equal to mc1 sin HMX plus MC2, sorry, M theta 1, M theta 0, this plus MC2 cos HMX. So, the value of d theta by dx at x is equal to 0, that will come as MC2 cos HMX. Sorry, x is equal to 0, x is equal to L needs to be put, x is equal to L, sorry, x is equal to L. So, that will be equal to M theta 0, M theta 0 sin HML plus MC2 cos HML. As the boundary condition B said, that is equal to 0, that means M theta 0 sin HML, that should be equal to M minus MC2 cos HML. So, the value of C2 comes as minus theta 0 10 HML. So, the integration constant C2 has a value in the present case if the farthest A end is fully insulated. So, C2 is equal to minus theta 0 10 HML. So, the expression for theta, thus the transformed expression for theta, that is a solution, can be given as theta is equal to theta 0 cos HMX plus C2, that is minus theta 0 10 HML into sin HMX. That can be further written as cos HMX into cos HML minus sin HMX sin HML divided by cos HML. So, we can write theta, that should be equal to theta 0 into cos HML minus x divided by cos HML. Let it be equation number 1. This equation number 1 represents the temperature distribution for the present special case, So, in this condition as well, we have to evaluate the next thing, that is the quantity of heat energy which can be lost by the fin in such type of circumstances. So, the expression for heat lost, or heat flux, heat lost, heat flux, that is equal to Q, that will equal to minus K into AC, and the expression is d theta by dx at x equal to 0. Now, evaluate the first quantity d theta by dx, that is equal to theta 0 divided by cos HML into the differential coefficient of this minus sin HM L minus x into minus m into minus m. That is equal to m theta 0 sin HM L minus x divided by cos HML. So, the value of d theta by dx at x is equal to 0, that is equal to m theta 0, this will be 0. So, 10 HML. Hence, expression for Q is equal to K A C m theta 0 10 HML. This is the desired expression for heat flux in the case of with one end insulated. That means the end which is present at the x equal to L is fully insulated. Now, this equation number 2 equation number 2 it can also be used for hollow tube instead of rods. That means, in the previous class, while considering the circular fin, we have considered the circular fin that is a full solid circular fin. So, in the present case today, instead of rods, this equation can be used for the hollow tubes also. And in this case, expression for m can be given as m is equal to h upon k into circumference of tube divided by cross sectional area of tube raised to the power half. This is the expression for m. Now, taking the plan view of this hollow tube, we can say that let us suppose this is the center. So, this is d naught, that is the diameter of the outer ring, and this is the diameter of inner ring, and this is called d I. Okay. So, it can be written as h upon k into circumference of the tube, that is equal to pi into d naught divided by cross sectional area of the tube. If the thickness is delta, if this thickness is delta, in the now that delta is the elevation view. So, that will be equal to circumference cross sectional area of the tube, that is pi d into delta raised to the power half. Okay. No, that is in the plan view itself. The plan view itself, that is the delta. Now, let it be question number 3. Let it be question number 3. Let it be question number 3. Now, as per the plan view, of hollow tube shown in the figure, how this do and di can be interrelated with each other? We can write d naught, that is equal to di plus 2 delta. We can write d naught, that is the outer diameter of the ring, that should be equal to inner diameter of the ring plus 2 delta. This and this much needs to be added with this to arrive at this quantity. And if di is much greater than 2 delta, then this quantity di plus 2 delta may be approximated equal to di. So, the equation 3 takes the shape as m is equal to h upon k into pi d naught divided by pi di delta raised to the power half. That can be written as h upon k into d naught, pi d naught. D naught is approximately equal to di. So, that is equal to pi di divided by pi di delta raised to the power half, that is equal to h upon k delta raised to the power half. Let it be question number 4. Now, let us make a discussion about the question number 4. Question number 4 is of immense technical importance, because in most of the cases the actual heat loss by the fin is always lesser than the actual heat dissipated. So, if I am saying that the heat flow in actual sense is always lesser than the total heat dissipated as calculated by the equation number 3, perhaps equation number 3, sorry, equation number 2. So, what does it mean? It means there is some error in the temperature measurement. This means that there are some errors in temperature measurement. Generally, on the live scale as well, as you go through the experiment number 6, I think, that the response of thermocouple in the transport phenomena lab, you will find that there is a lot of variation in the temperature actually measured and measured from the experiment and the actual temperature. There is a lot of differences there, you will find, because that is the case of the unsteady state heat transfer, that when the cooling and the heating curve both becomes asymptotic to the time axis after some time. So, we will find a lot of temperature measurement errors are there. So, this equation has the importance that when you using a thermometer valve in order to measure the temperature, the error in that temperature can be calculated by this factor, that is m equal to h upon k delta raised to the power half. So, equation number 4, discussion on equation number 4. Equation number 4 this equation can be used to measure the error in the temperature measurement, by a thermometer valve, This is of immense technical importance. Since heat flow in actual sense is always lesser than the total amount of heat energy, dissipated by the fin. So, by utilizing this equation, you can easily measure the errors in the temperature measurement, and applying that correction factor, a reasonable level of convergence can be obtained in both the cases. That is, the heat dissipated in the actual sense and heat dissipation calculated as per the fin equation, and they are more or less, then they become equal. Now, let us come to the second case. The length of the fin is very, very long or infinite. Let us try to discuss the second case, case number 2. Case number 2, the fin is sufficiently long or infinite. What does it mean? That is the L tends to infinity. The boundary conditions now then are number A, first boundary condition will not change, that is theta equal to theta naught, that is instantaneous temperature difference, that is the temperature difference at the root for the steady state heat flow, that is equal to at x equal to 0, and the boundary condition number 2 is theta equal to 0. That means if the length of the fin is very infinite or very large, that means it can be said that at the extreme end, that is at the infinite end of the fin, there is no temperature difference that is there between the temperature of the fin and the temperature of the ambient air. So, T minus T A is almost equal to 0 at x equal to L, at x equal to L, L being very large, L being very large. So, as usual, the value of C1 will come as theta naught as previous. So, C1 equal to theta naught, and C2 that you can arrive here, that is equal to minus theta 0 cot HML. Try to evaluate this theta 2 by yourself. You can easily arrive at C2 equal to minus theta 0 cot HML. So, the expression for temperature profile, is theta equal to theta 0 cos HMX minus C2 sin HMX. So, theta C2 minus theta 0 cot HML into sin HMX. So, the value of d theta upon dx, that is equal to theta 0 m sin HMX minus m cot HML cos HMX. So, the value of d theta by dx at x equal to 0, that is equal to theta naught, this is equal to 0 minus m cot HML, that is equal to minus m theta 0 cot HML. So, the expression for heat lost heat lost by the fin is given as Q is equal to minus K into AC into d theta by dx at x equal to 0, that is equal to minus K into AC into minus m theta 0 cot HML, that is equal to K AC m theta 0 cot HML. Now, putting the limiting condition, Now putting the limiting condition. So taking the limiting condition as L tends to infinity, then cot HML will tend to 1, cot HML will tend to 1. So the expression for Q comes as, thus Q is equal to KAC m theta 0. Putting the value of m here, you can write KAC m square is equal to pH upon KAC. So this into theta 0. So that will come as under root KAC P into H into theta naught. Let it be question number 3. This equation number 3 is the expression for the heat lost by the fin if the length of the fin is infinite. So the next important thing is to understand the efficiency and effectiveness of fin. So efficiency and effectiveness of fin. This effectiveness of fin is defined as effectiveness of fin. This is denoted by the Greek letter epsilon. It is defined as epsilon, that is the fin effectiveness, is equal to heat lost in the presence of a fin material divided by heat lost without fin. Heat lost in the presence of the fin material divided by heat lost without fin. This is the quantity which is denoted by the Greek letter epsilon and which stands for the defining the effectiveness of fin. Later on, while discussing the unsteady state heat transfer after 1 or 2 to 3 classes later, a new dimensionless number will get introduced to it, that is called Buyout number. That is basically defined as H by K into delta, that is delta is the characteristic dimension, H is the convective heat transfer coefficient and K is the thermal conductivity of the material. So that by this ratio is a function of Buyout number. This Buyout number is defined as H delta by K. It can be written as H upon K divided by 1 upon delta, delta upon K divided by 1 upon H. It is defined as internal resistance of the fin material, because thermal conductivity term is there, internal resistance of the fin material divided by external resistance external resistance on the fin surface due to fluid. What is fluid here? That is the air. So, as I have said earlier that this is a conduction convection system, the extremity of the fin end that is exposed directly to the environment. So, the ambient air is the fluid which is taking part in this convective mode of heat transfer. So, this quantity is called the internal resistance of the fin material, whereas this quantity 1 by H is denoted as external resistance on the fin surface due to the fluid present in as the ambient air. So, this quantity is this. Another quantity, that is the effective efficiency of a fin, this is denoted by another Greek letter eta. It is defined as heat lost from the fin, divided by heat lost from the fin when the entire surface of fin is maintained at root temperature. Root temperature, that means the temperature which is prevailing at at the base of the fin, that is at x is equal to 0 or L is equal to 0. So, this is called the effectiveness of fin. Depending upon these two decisive quantities, that is the effectiveness of fin and the efficiency of the fin, as well as this Buyout number, different cases of the use of fins in the industrial practices can be tabulated. I will give you the analysis in the form of a table to discuss the various conditions which may prevail on an industrial shop floor, and you can easily decide that when such type of conditions prevail on an industrial shop floor practice, during your practice, how can you design a fin. So, the various cases, that is case number 1, case number 2, we will discuss the 3 cases one by one. Case 1 is epsilon is equal to 1, that is the fin effectiveness is equal to 1 and Buyout number is equal to 1, that is the H delta by K is equal to 1. So, in this case, when this condition prevails, so in this case there is no use of fin, and hence or you can say the fin may not be required in this case, and the second one is possible. The second condition in which this is possible when the fin material is a bad conductor of heat energy, when either of two conditions or two conditions side by side, when these two conditions prevail, in those circumstances epsilon is equal to 1 and Buyout number is equal to 1, and when this condition prevails, then there is no use of using any fins. Case number 2 is epsilon less than 1 and Buyout number is greater than 1. When this condition prevails, adverse effect will be there. If fin is used. So that means adverse effect on the heat flow will be there if in these circumstances, if you are utilizing an fin. And the point number B, in the case of steam pipes, or steam condenser tubes, where steams are being condensed. In the case of steam condenser tubes, fins are not used. The value of convective heat transfer coefficient in such cases are very, very large. And due to this fact that if the value of H is very, very high, then there is adverse effect on the heat flow if you are utilizing a fin. Case number 3 is epsilon is greater than 1 and the Buyout number is less than 1. This is the most prominent case, a most desirable case for using fins. Most desirable case for using the fins. This is possible when the fin material is a very good conductor of heat energy, that is possible in the case of FCC metals, face centered cubic metals, example copper, aluminum, etc. So, we have gone through the discussion that under which circumstances the fin should be used and under which circumstances a fin is not recommended from an engineer. So, we have gone through that. In the next class, here the important assumption I would like to emphasize in the previous class where I have conducted the heat flow analysis from a rectangular fin. The assumption was there that the heat flow is unidirectional in nature. In spite of the fact that the rectangular fin is 3-dimensional in view, but we have assumed there that the heat flow that is taking place is unidirectional, that is along the x axis, that is the perpendicular to the area, perpendicular to the cross sectional area in the heat flow direction. So, that assumption you should incorporate there, that the heat flow was unidirectional in nature. In the next class, we will try to discuss the 2-dimensional heat transfer, especially the Laplace equation, and we will try to solve the Laplace equation in some cases, that how the Laplace equation for the 2-dimensional cases, that is d by 2t by d by x2 plus d by t2 d by y2 for a 2-dimensional surface, that is equal to 0. So, we will see that in the later class. Thank you.